Hi everyone, thanks for attending. So I'm very happy to be here virtually and share my personal, maybe biased view of open problems in learning in federated settings. Yeah, as Nick said, my name is Tian, and I'm about to graduate at Carnegie Mellon University. And I'm going to join the University of Chicago as an assistant professor starting from next year. So, okay. Yeah. So machine learning heavily relies on data in various applications. And where does data come from? They can come from the devices or clients or sensors. And more frequently, they are generated by and settled across not just one, but networks of many remote devices or organizations. Right. So I guess the audience here are more or less already very familiar with federated learning. For example, we want to jointly train a model to predict the next characters across a number of smartphones. But sending sensitive and sometimes real-time user data to some data center may not be allowed or can be very costly. So it's important to enable access to such large amounts of data without moving all of them to one central location. So learning across networks of decentralized data while keeping all of them local is very important because it can help protect sensitive user data and data ownership, avoid expensive or even prohibited raw data transmission, and boost the effective sample size by collaboration, right? So one critical learning framework that supports data sharing is federated learning. And it has been deployed by a number of service providers and real-world applications in different areas. And of course, including those empowered by Flower. Okay, so before I jump into the open problems of federated learning, I would like to briefly start with some of the challenges of federated networks and how does it differ from the classic distributed learning. Okay. So usually we have a central server and a bunch of remote devices communicating intermediate information with this central server periodically to jointly learn some statistical models. So there are a set of unique challenges and properties. So the entire systems are very heterogeneous due to the variable hardware of the devices, the network conditions, and so on. And then each device generates local data following a local distribution, which can be very different from each other. So you can imagine that different users may have different styles of using their phones, for example. And the user data are not identically distributed. And this data heterogeneity issue can affect the training pipeline a lot. In communication can be a real bottleneck, especially across massive, unreliable device wireless networks. And also privacy is a major concern. So federated learning takes some initial steps towards protecting user privacy by minimizing data exposure in the system. So it never transmits the raw data. So it just minimizes the user data. But it's not inherently secure or private. So we always need additional mechanisms on top of it to guarantee some specific notions of privacy or security. Okay. So under these practical constraints, to deploy federated learning in practice, there are usually many metrics that we care about. Right? Maybe the first and the most important one is accuracy. So how do we optimize in such heterogeneous and communication constrained environments? Right? So how to make sure that federated methods can converge to the correct solution efficiently under data and systems heterogeneity. And so beyond accuracy, because federated applications aim to learn over massive client data using client devices as distributed computing nodes, there are critical constraints regarding trustworthiness. For instance, fairness against client sampling bias, representation bias, and data imbalance, and robustness to device failures, to real-world data noise, training time attacks, and so on, and privacy. Right. So there are lots of extensive previous research that have been done to address different challenges and constraints in federated networks. And this is definitely not a complete list of the things that people have considered. So for instance, in terms of accuracy, a ton of research have been done on federated optimization, various optimization techniques, either first order, second order with adaptivity or with variance reduction, or decentralized, centralized, and so on. And then they have different assumptions under different settings and different ways of model the data heterogeneity across the network. And in terms of fairness, I think previous works have considered different notions, such as algorithmic fairness, which is closer to the classic fairness notion in the broader machine learning literature, where people care about the statistical independence between the protected sensitive attributes like race or gender and the predictions. And also representation disparity to make sure that the model can perform well for all populations of the clients. And also proportional fairness, basically you get what you contribute. And I've also considered robustness to distribution shifts and to inference time and training time attacks. In terms of privacy and security, there are many either generic or sometimes more application-specific privacy notions, such as differential privacy, which is a very rigorous framework to measure and guarantee to measure privacy in different optimization techniques in different scenarios, convex and non-convex settings. Yeah, so, and this is my research at the intersection between optimization and trustworthy learning, while taking into account and rigorously considering the practical challenges such as heterogeneity and communication. In terms of the open problems, I think there are general the problems that are more specific to federated learning and then open problems for general ML. And then oftentimes the methods that we develop for federated learning, so sometimes they can be generalized to solve general machine learning problems. And on the other hand, we can always adapt general machine learning problems for federated learning. And there are 4 or 5 directions I want to mention next. So one is about new applications and workloads of federated learning for data sharing. So starting from the existing federated learning techniques, I think one kind of slightly underexplored direction is about the cross-silo applications where communication may not be a constraint anymore, and each client may have enough local computation, and sometimes the constraints are more on the privacy and security side. And these cross-silo applications can allow for the use of more expensive algorithms, and sometimes it may also involve feature parallelism. I think this is generally less explored compared with the cross-device applications where we jointly learn across remote devices like sensor networks. And we can also extend and adapt the current methods that are specifically developed for federated optimization to distributed training in data center environments. For instance, we have developed lots of methods for based on local HDD style of updates for federated optimization. And that is motivated by federated settings. But the local HDD type of optimization algorithms can also be used for data center training. For instance, training large models across hundreds of GPUs or TPUs, efficient optimization. And also, I think it's important to think about leveraging public data or public information to improve the current federated learning algorithms and systems. So for instance, one way to do that is to use the pre-trained models. And use that, we may need to revisit lots of the current assumptions and conclusions of our current algorithms. Okay, so one kind of challenge there is to enable this on-device training or on-device personalization of large models efficiently. And another direction, I think is a fundamental problem, is to perform diagnostics of the federated networks and adapting to data heterogeneity. So the current approaches are very expensive because one fundamental constraint there is that the server cannot see the raw data. So usually we can use gradient diversity across all the data points or some loss differences across all the clients or form some task relationship regularizer to model the data heterogeneity. But especially in the cross-device setting where we have potentially thousands to millions of devices, those approaches can be very expensive. And the questions there are how to perform diagnostics, ideally before training in an efficient way. And related to that, an additional question is, how does heterogeneity look like in real federated networks? So we potentially have many applications that require data sharing in a secure and efficient way. But then just sometimes we need more applications and benchmark tools to help us really understand this. I think there are lots of great works on benchmarking federated environments and different applications, but we still need more. And in the future, there are also other fairness and robustness notions that we need to consider beyond what has been already studied. So that may involve considering different stakeholders, including users, model engineers, and policy officers. And given many fairness or robustness concerns, how do we solve them efficiently in a decentralized way is also very open. And so we need to push the existing rigorous fairness and robustness works that are developed for just centralized or normal machine learning for maybe convex problems or homogeneous settings to heterogeneous and stochastic environments. And there are rich interplays of fairness and robustness with other metrics like privacy and incentive mechanisms. So how do we incentivize clients or potential participants to join federation? Okay. And another question is, for example, can we understand the relations between robustness and privacy? Right? Because sometimes distributional robustness robustness to distribution shifts. To address that, we need to reveal, additional information which may be at odds with privacy. So how can we understand that rigorously? Can we develop better methods for that? Okay, so I think a very big open problem is around the area of privacy and security. And specifically, one angle is to narrow the gap between privacy theory and practice, both for federated learning and also this is also very open for general machine learning. So the current differential privacy definition is very pessimistic because it's defined in the worst case. So it's important to explore other relaxed privacy notions. For example, in the context of federated learning, we need to consider user-specific privacy laws or data-dependent, feature-dependent privacy. And sometimes we may guess privacy for free benefits from some of the existing randomized algorithms that are not designed for the purpose of privacy. But because it has some randomness, we may get some privacy benefits out of it. So those are about relaxed privacy definitions. On the other hand, given any privacy definition, previous works, they have extensively studied privacy optimization, but for very limited algorithms or very limited settings like stochastic gradient descent for centralized machine learning training or for Fed average. So I think exploring how to guarantee differential privacy for more than machine learning tasks is also very interesting. One is to consider integrating privacy with advanced optimization methods. For instance, adaptive optimization and robust optimization. And in multitask, this distributed environments, right? And then under distribution shifts. So can we guarantee privacy and handling distribution shifts at the same time? So lastly, I think it's also very open to think about how to jointly address scalability and trustworthiness. So there are many open problems in the interconnections among various metrics, like the interplays between privacy and robustness and generalization. And one question is to develop methods to simultaneously satisfy those joint constraints. So I think one promising direction is to use personalization. And the question there is to understand how can personalization help in terms of what specific metrics, and can we formalize that, and can we rigorously understand that? And then in terms of the evaluation, I think we need to evaluate in the trade-off space to jointly consider the two-way or three-way trade-offs between the different metrics to ensure that the progress are meaningful. So the progress lie in, so they will push the Pareto front compared with just exploring different solutions. Maybe they are all in the same Pareto front. Yeah, so I think that's all I have. I'm happy to take questions and discuss more.
So we deliberately designed this session to sort of leave ample time at the end to get questions from the audience, so we can try to explore a few issues, some of the ones that you raised and maybe some of the ones on the minds of our audience. So I guess I'll first ask the physical audience here. Anyone have a question or a direction they want to sort of put forward? Or online? There's one from Daniel. I'll just come over here.
Hi, first of all, thank you for the great talk. Really enjoyed it. I'm curious, how big do you think, or is there a gap between what we can simulate in research and what we see deployed in production, in terms of all of these questions that you brought up, and how close can a simulated research system get to the kinds of challenges that we see in a production system at maybe Google or Meta scale?
I think that's a great question. So I think in terms of the scalability, so I think there is not a large gap between what research labs can do in terms of the computation or simulation capabilities. So for instance, I think current benchmarks that are developed from the from academia, I think lots of them involve maybe millions of the clients that are in the data set. I think that's kind of close to what people see in industry settings. And I think one potential gap there is about the use cases and the applications. For instance, there is this direction of federated learning where we just mostly focus on learning-based tasks, but there's also another line of research and what people are doing in industries focusing on analytics tasks, so things not necessarily learning, but some analytics. So for instance, heavy hitter estimation, quantile estimation, clustering, and so things like that. And those are sometimes very important for real applications, but then not explored a lot for academic environments. I think partly because we don't have a very good knowledge of the real applications there. So I think that's one area I think people in different communities can collaborate more on.
Great. I think I saw a question come through Zoom. So
the question is, could you kindly provide book or any useful resources suitable for beginners?
Yeah, so I think there are a lot of useful resources online developed by different groups of researchers or practitioners. So as far as I know, I think there's a NeurIPS tutorial. I think in NeurIPS 2020. Yeah, there is a federated learning tutorial with videos. I think that can be a great resource. And also, I think there is some survey paper written by my group, and there's also another some other survey papers. I think there's one written by Google that's much longer, and there are also some other survey articles. I think those are all great resources.
Great. I think we might have one more Zoom question I saw come in. Am I correct?
Thank you for the great talk. What are your thoughts on personalized federated learning settings? Do you believe it holds more promise in a cross-silo or cross-devices environment?
Okay. Yeah, I think personalized federated learning is very important for both settings. So one is that it can, like as expected, personalize. By doing personalization, we can improve the performance or accuracy of the models across the clients. And I think some of the recent research have also been discussing some other benefits of personalization in regard to other metrics such as fairness or robustness. So by naturally adapting to the data distributions and modeling the heterogeneity properly, I think it will have more benefits later that we can explore more.
I see we've got three questions in the room right now, which is very exciting. I'm going to take them in order. We do have time as long as they're quick.
Thank you so much for your work and all your contributions to the field over time. I'm very curious about your thoughts on the differential privacy guarantees we can get from randomization of algorithms. Can you share any more details, or also where to kind of learn more about kind of what you think of as state of the art in that area right now?
Oh, thanks. I think that is still pretty open. And I cannot say like which paper or which particular work is the state of the art, but my personal thought is that so for instance, one type of randomized algorithms is based on linear sketching. So we just compress the gradients and then maybe sketch them to some randomized tables, and then sometimes, I think oftentimes that is used not only in federated, but also in other domains for efficiency purposes, because we can have a very small output from a potentially very large gradient. But then because that process is randomized, I think the additional noise introduced in that can have privacy benefits if we can understand that. Yeah.
Thanks a lot for the talk. It was very interesting. Since we're speaking about open problems in FL, I was wondering how efficiency, model efficiency or training efficiency fits into this picture. What's your take on, do you think it's a solved problem, or do you think it's not? And what would be your take on future directions regarding this?
Yeah, I think it's also important an open problem there, especially we have observed the great success of large models and especially generative models in different domains. And then I think one constraint usually for federated learning is the computation capabilities of the devices, especially for cross-device applications. And how do we do large model training in federated setting? It's not very clear, right? So one way is that we can have a large model at the server side, and then the client will only interact with the server by updating some client-specific parameters, which may be a very tiny subset of the model parameters of that large model, so that can improve the efficiency. But then that's just one way, and then there are potentially many other ways of doing this efficient and maybe low precision or maybe compressed training to scale federated learning to support more applications. Yeah.
Thank you. But there's also another great answer. We're sort of a bit low on time, so we're now going to move on to our next part of the summit. But again, I just wanted to say thank you so much for coming this morning. For you, this afternoon for us to share your thoughts and for all the great work you've done in federated learning. Thank you.
Thanks everyone. Feel free to contact me later if you have any questions. Yeah.